Hello, in this video I will do Calculus 1 final exam limit section. So this is a final practice, a final exam for Calculus 1, and this will be on limits. So before we do some problems, let's kind of review some limit rules. What I would do first, what I would do is just plug it in and simplify. If your x value is a real number, go ahead and plug it in. If your function is a rational function, step two, if you do plug it in and you get an indeterminate form like 0/0, or if you have a 0 on the bottom, it's an indeterminate, then you would do a few things from there. What I would do first is, if it's a polynomial, I would probably factor, right? And if you factor, something might cancel, then it might work. If you can't factor, try finding a common denominator if you can. Another one is you can multiply top and bottom by the so if you have a rational function or anything with a square root, what I would do to get rid of that square root, I can multiply top and bottom by the conjugate of the denominator. And then if you have some trig rules, you can do, for example, the trig rules sine of ax over bx or cosine of x minus 1 over x. So, or you could just do L'Hopital's rule. That would work as well. Yeah, or like I said before, if all fails, you can always do L'Hopital's rule. If your limit and your axis is going from positive to a negative infinity, you are analyzing end behavior, and you are basically finding the horizontal. So horizontal asymptote, and we'll go over those rules if we need to. You can also recognize the limit of definition of a derivative. So the limit as h approaches 0 of f of x plus h minus f of x all over h equals f prime of x. Or you can use this rule, limit as x approaches a of f of x minus f of a all over x minus a is equal to f prime of x. So let's start with question 1. It says, find the limit as x approaches 0 of this rational function 5x cubed minus 3x squared minus x over 15 minus 7x cubed. So first, maybe I could just get away with plugging in 0. So let me try it. Let me just plug it in. Let's see if we have an indeterminate form or not. So where we see next, plug in 0. So this is going to be 5 times 0 cubed. And lo and behold, you get 0 over 15. And 0 over 15 is not indeterminate. It's actually real. It's 0, which is a real number, which is good. So it's not indeterminate. It works. If you plug it in, I got a real number. 0 is real. Your limit is 0. Okay. So yeah, sometimes it does work. Sometimes just plugging it in, you can get away with it with plugging it in. What about 2? The limit as x approaches 0 of this rational function, x squared plus 2x over x squared minus 2x. So first, maybe just plugging it in might work. So this is going to be 0 squared plus 2 times 0. Let's see what happens. We get 0 plus 2 times 0 is 0. Bottom 0 squared minus 0 is 0. And unfortunately, you have indeterminate. Which is not good. So you have options. What would I do? what could we do? So what we could do is it is a rational function. Maybe we could factor out a common denominator. So the first thing I would do is try factor. Okay, so let's do that. So the limit as x approaches 0. And let's look at the top, x squared plus 2x. It looks like you could factor out an x. So this is going to be x plus 2. And then on the bottom, x squared minus 2x, it looks like you can take out an x. That's x minus 2. And what do you see that cancels? I see the x's cancels. Okay, now we have a new problem. So we're going to rewrite it as the limit as x approaches 0 of our new problem, which is now going to be x plus 2 over x minus 2, right? Now we can just try chugging it in, and let's see what we get. So it would be 0 plus 2 over 0 minus 2. 0 plus 2 is 2. 0 minus negative 2 is negative 2. Look, it works out. 2 divided by negative 2 gives us a real number. That's what you want, a real number. And yeah. What would you, if you didn't know how to factor it, or if you forgot, what's another option you can do? Another option you can do is you can also use L'Hopital's rule. So let me just write that out on your notes. Note, you could also use, because it is a fraction, you could use L'Hopital's rule. So what you would do for L'Hopital's rule is go back to the original and then just take the derivative of the numerator and denominator, maybe just once. If you have to do it again, that's fine. Sometimes you have to do it more than once, but in this problem, I think you could just do it once and you will be fine. Okay, let's move on. Oh, let me just show you yeah, so basically let me show you really how to do the L'Hopital's rule. You just take the derivative of the numerator and denominator. So the derivative, go back to your original. The derivative of your original of the numerator would be 2x plus 2. And then the derivative of the bottom of the original would be 2x minus 2. Then go ahead and plug in 0 for x. So this would be 2 times 0 is 2 over 2 times 0 minus 2. And you get 2 over negative 2, which is negative 1. Perfect. See, L'Hopital's rule would work. Not too bad, right? We could, or not too bad. Let's look at example 3. We have the limit as x approaches 8 of the rational function x minus 8 over 3 minus square root of 1 plus x. I immediately see that if you try plugging in 8, it's a big no, right? Because it'll make the bottom 0, right? Square root of 1 plus 8 is 9. Square root of 9 is 3. 3 minus 3 is 0. So that's a big no. Yeah, here. If I just try chugging it in, eight minus 0 is 0, and then this would be 3 minus square root of 8 plus 1 is square root of 9, 0, and 3 minus, yeah, this is an indeterminate form, so that will not work. What could you do? Several things you could do. You could try doing L'Hopital's rule, but I see it's irrational, and then there's a square root. The minute I see a square root, and it's a rational function, I automatically assume you can do the conjugate. So that's what I'm going to do. I'm going to multiply top and bottom by the conjugate, and it's usually the denominator. So what would be the conjugate of the denominator? So it's just the conjugate of the denominator is basically the same thing of the denominator. The only difference is just the opposite sign. So instead of minus, we're going to use a positive, right? So we're going to do x minus 8, and then it's going to be 3 minus square root of 1 plus x. I'm going to multiply top and bottom by the conjugate, so it's going to be 3 plus square root of 1 plus x. 3 plus square root. Okay. And what I would do is, what would I do? I would not FOIL out the top. I would just leave it as it is. You'll see why. So just leave the numerator alone. So it's really x minus 8 times 3 plus square root of 1 plus x, right? The only thing I would do is I would simplify the bottom. And there's a shortcut. They're practically the same thing. The only difference is this is a minus and this is a plus, right? So if they're the same thing and there's a minus and a plus, it's a perfect square. So basically, it's a squared minus b squared. And our a is going to be 3 minus, and my b is going to be square root of 1 plus x. Okay. So let me clean that up. Let's see what we get. So the numerator, I'm just going to leave that as it is. Do not FOIL it out. Just leave it as it is. Okay, on the bottom, if you do some algebra, 3 squared is 9 minus, when you square a radical, the radical disappears. So you're just left with 1 plus x. And then you FOIL out this minus, so it's negative 1 minus x. And then you have a 9. And then 9 minus 1 is 8. And minus 1 is 8 minus x. Okay. If I chug in 8 already, it still would make it indeterminate form. It would make the bottom 0. But there's something else I could do. Do you see this x minus 8 on the top, and then on the bottom it's an 8 minus x? Are they the same thing? No, they're not, but they're almost the same, right? What we could do is kind of manipulate. I guess you can manipulate either or, but I'm going to manipulate the 8 minus x. I can rewrite 8 minus x as negative 8 and negative x plus 8. But it's still not the same as x minus 8. So what I would do, I can't really change the problem, but I can, adjust it. It can't be, so what I would do is on the bottom, I could factor out a minus. So I would factor out a minus, and then this is now going to be positive x, and then this would be negative 8. I haven't changed the problem a bit. I just kind of, readjusted it. If you FOIL out this negative, it's still going to give you 8 minus x. So that's really important. You can't really change it. You can just rearrange it a bit. So it's going to be the limit as x approaches 8. And then on the bottom, it's going to be minus x minus 8. And then what do you see that cancels? The x minus 8 cancels because now they're the same. And now we can rewrite our new problem. And then there's still a minus right here. You either put the minus on the top or on the bottom. It doesn't really matter. Now let's see what we get when we plug in 8. So it's 3 plus square root of 1 plus 8 over negative 1. That's 3 plus 8 plus 1 is square root of 9 over negative 1. And then 3 plus square root of 9 is 3 over negative 1. 3 plus 3 is 6 over negative 1, which is negative 6. And then you could have also done L'Hopital's rule, just take the numerator, the derivative of the numerator and denominator. Okay. Let's move on to next example. Okay, example 4, we have the limit as x approaches 0 of 2 sine of x over x. First step I would do is just try plugging it in. Do that. It's 2 sine, wherever you say next, plugging 0. Got a problem, right? Zeros on the bottom can never, it's in determinate form. Sine of 0, 0 times 2, that's 0 over 0, which is indeterminate form. So what could we do? There's a few things we could do is we can use our trig limit rules. And yeah, you could use this rule. So this is this is a special one too. Like, okay, so this would be the limit. Your special trig identity limit rules are these. Sine of a of x over b of x is equal to a over b. Or you could think of it as the limit as x approaches 0 of sine of x over x is equal to 1. So do we have this? We almost do. We have this. We have sine of x over x, and that should equal to 1. And then you have this 2. So your final answer should be 2. So what I would do, yeah, all we got to do is like factor out that 2. Because we want it, we can use this rule, but we don't have that. We have this extra 2. So what we'll do is, it'd be the limit as x approaches 0, and then just factor out that 2. We know that the sine of x over x is 1, so this is going to be 1. So it's really 2 times 1, which is 2. Okay, let's move on to example 5. Okay, example 5 says, find the limit as h approaches 0 of sin of 5 pi over 6 plus h minus 1/2 all over h. So what we could do is, we could use L'Hopital's rule. We could also use the limit definition of a derivative. So yeah, that's what I'm going to do. I'm going to do the limit. So the limit as h approaches 0. So this is the limit definition derivative. I'm going to rewrite it as this. So this is our limit definition. Do we have, let's see. What is our x? Our x is going to be, here, let me show you. So look at what we have and compare it with this. So it looks like our x is 5 pi over 6, right? If you compare this with the limit definition, our x is 5 pi over 6, and we have our h, which is just h, and our f of x, I believe our f of x is going to be sine of x, right? This is your f of x, and yeah, our, our f of x is definitely going to be sine of x. Okay. Let's find f prime of x because part of it says we need to find f prime of x, so let's find that. So f prime of x is, what's the derivative of sine of x? It is positive cosine of x. Okay. And wait a minute, why is x 5 pi over 6? Reason why is since the sine of 5 pi over 6 is equal to 1/2. And we also have a coordinate. If we plug in f prime of 5 pi over 6, that's what we also need. It's going to be equal to cosine. So f prime of, so we know our f and we know our x is 5 pi over 6. According to, let's find f prime of x. So f prime of 5 pi over 6 is the same thing as cosine of 5 pi over 6. And when you take what is the cosine of 5 pi over 6? That's quadrant, I believe, 2, so that would be negative radical 3 over 2. So if you use the limit definition of derivative, your answer will be negative radical 3 over 2. Another option is you could use L'Hopital's rule. Okay. Okay, let's move on to example 6. Okay, example 6, we have this kind of piecewise function. We have f of x equals ln of x, where the x is, where for the function L of x, we have this piecewise and L of x, and we can only go from 0 to 2, where 2 is included. And then your other function is x squared times ln of 2 minus ln of 8, where we can only go from 2 to 4, where 4 is included. Oh, and then it says, and then the limit, I didn't write this down, but this is part of the problem. Then the limit as x approaches 2 of f of x equals to what? So what does that mean? What is the limit as x approaches to f of x? It implies that the limit must come both directions, and you got to plug it in both equation. So what you don't see, if this is dealing with one-sided limit, um, you don't see a plus or minus two, but you have to do it because it's a one-side limit. So let me write this down. It implies must come in both direction. Got to plug it in both directions, in both equations. So that's what we're going to do. Let's plug it, let's plug into the first equation. So let's do it. So what we're trying to say is this. Does in the first equation we have ln of x. So if you plug in ln 2, plug in the x value 2, does that equal to this equation where the x value is 2? So that would be 2 square times ln of 2 minus ln of 8. Okay, is that true? If it is true, then uh, and f of 2 equals to that. If it's true, then whatever, then f of 2, it would equal to ln of 2. Let's adjust. So let's do some algebra. So on the left, ln of 2, there's nothing much we can do. It's just ln of 2. On the right, let's do some algebra. 2 squared is 4 times ln of 2 minus ln of 8. You're probably thinking that does not equal to the left side, right? Well, we're dealing with natural logs, which is technically logs. So what you have to do is kind of like, what's the word? Not expand, but condense it into one natural log. Because it's a, yeah, see how they both have a natural log. So over here for ln of 2, if you recall, if you have anything, if you have the number in front of the 4, if it's in front of the log or natural log, what does that really mean when you're condensing it? It's a power. So this could be expressed as ln of 2 to the 4th power minus ln of 8. What else could we do? So this would be 2 to the 4th is 16 minus ln of 8. And then can you make this into one single natural log? Yes, you can, because a minus means when you're condensing, it means dividing. So this could be ln of 16 over 8. And then you could simplify 16 over 8, which is 2. Hello, you got the left side, right? The right now equals to the left. So you can say the limit as x approaches 2 is equal to ln of 2. That would be your final answer. I know what you're thinking. If I go back to our problem, why can't I just plug in 2 into the first one because our domain values? That's technically true, you could, but you have to make sure that the limit must come in both directions. That's why I had to plug it in both equations. So I guess you're right. You just plug it back into the first equation because of the domain, but this is how you would show the work. Let's move on. Example 7. So example 7, we have the limit as n approaches infinity of this rational function 6n cubed minus 5n over square root of 4n 6 minus 2n squared plus 1. What could I do? I could just try chugging it in. See. Oh, sorry, that's the wrong note. I was no. Well, yes, I can. I just have to be careful. My n is not a real number; it's infinity. So I thought it was going to be zero, but it's infinity. So let's just plug it in. So it's going to be 6, and then where we see an n, replace it with infinity. What do we get? Infinity cubed is infinity times 6 is still infinity. So infinity minus another infinity, or a smaller infinity, it's infinity minus infinity is not 0. It's actually infinity. Because this, I think this is a large infinity minus a small infinity. So that's still infinity. And then on the bottom, this is still going to be infinity. What's a squared infinity? Still a fairly large infinity number. You still have uh, you have indeterminate form. You can't have infinity over infinity. That is bad. So let's go back to our drawing board. What could we do? Well, what kind of equation do we have? This is a rational function, and our x value or our n value is not a real number, it's infinity. So you're dealing with rational functions and you're dealing with the x is infinity. So that's how I know it's related to a horizontal asymptote. So your limit is your horizontal asymptote. So this is where you're going to need your three rules for horizontal asymptotes. So what you're going to do is, so what is our horizontal asymptote? It's y equals, and then what you do is pick the highest term on the numerator. So our highest term is in the numerator is 6n cubed. And then what is the highest term on the denominator? Now it is not 4 and 6. We're taking the square root. So if you took the square root of 4n cubed, it's 2. And then what's the square root of n6? N cubed. So, and then if you take the square root of this is no longer going to be the highest, so you don't have to worry about these. So square root of 4 and 6 is going to be 2n cubed. And what do we know about the rules when the degrees are the same? You just use the coefficient. So if the degrees are the same, you're going to use coefficient. So your horizontal asymptote is going to be 6 over 2, which is 3. Okay, 7. So yeah, when you're dealing with rational functions and your x is infinity or negative infinity, you know it's going to be, your limit is going to be your horizontal asymptote. Number 8 says the limit as x approaches 0 of tan cubed of 2x over x cubed. So is a rational function and our x is 0, so we can't do the limit is your horizontal asymptote because it's not dealing with infinities. So I can just try plugging it in. And let's see what would I get. So I would get the limit. And then just replace x with 0. So 2 times 0. Yeah. Is there tan? Yeah, this is 0 over 0, which is indeterminate form. So big no no. So what we're going to do is what are we going to do? We could try using this is like, we could try rewriting it and somehow it'll be related to one of our trig limits, our special trig limits. I think it's going to be the limit as x, limit of sine of a of x over b of x. So I'll use that rule. So we're gonna try to use uh, limit as sine of a of x over b of x. Okay, so to do tan cube, that is what could we do? Yeah, tan cube, I think that's almost the same thing as tan of 2x times tan of 2x times tan of 2x, right? That's what I believe it. Yeah, I believe that tan cube of 2x is the same thing as saying tan of 2x times tan of 2x times tan of 2x. And then on the bottom, x cubed is fine. Now, could I simplify tan of 2x? Yeah, right? Tan is the same thing as sine over cosine. So yeah, we definitely can do that. So tan of 2x can also be expressed as sine of 2x over cosine 2x, right? So, and then we have this, and then you have three of them. So it can be sine of 2x over cosine 2x times sine. Okay, so what we're going to do is rewrite it as the limit as x approaches 0 of sine of 2x over cosine of 2x times sine of 2x. And then on the bottom, it's just x cubed. Um, let's see. So we're dividing each term by x cubed. So just for one of them, sine of 2x over cosine of 2x. If we just did one term, like divided by x, this is just one because we're dividing each term. X cubed is the same thing as x times x, right? We have a complex fraction. What would this be? Sine of 2x over cosine of 2x over x. The other is like sine of 2x over cosine of 2x. This is the same thing divided by x over 1. If I cross multiply, this would be sine 2x over x cosine 2x, right? Uh, mm, so yeah, that's pretty much what it, yeah. Wait, let me show you. You can also rewrite it like this. I'm running out of space, so I'm going to go on the side. So you could also rewrite this problem, like if you do all the algebra, You can rewrite this problem as the limit as x approaches 0. Sine of 2x. And then x cubed is the same thing as 1 over x times 1 over x times 1 over x. See, I have not changed the problem. I just readjusted it. So, uh, so what happens is when you do all the work, yeah, when you do all the work and then simplify this, this now becomes the limit as x approaches 0. And then somehow the sine x cancels, and then you're left with, so the x's cancels, and somehow the x's cancels, and then the signs cancels. Now you're left with 8 on the top. And then on the bottom, you're left with cosine cubed of 2x. Okay, so when you put that in, that's going to be 8 over cosine of q, and then 2 times 0 is 0. And we know that the cosine of just regular 0, just 1 0, cosine of 0 is 1. But there's 3 of them, so 1 cubed. That's 8 over 1, which is 8. Okay, so that one was tricky. And then what could you have else done is you could have also used L'Hopital's rule. I should have done that. I think that would have been a lot easier. So you would just take the derivative of the numerator and denominator maybe once or twice, and then plug in your x value 0. Okay, let's move on to example 9. So example 9 says we have a rational function of the x value 0 of this rational function x squared minus 2x cubed plus 3x minus 4 over 4x cubed minus 3x squared plus 2x minus 1. So what I would do is I would try plugging it in. Try plugging it in. So the limit as x approaches 0. Now wherever you see an x, plug in 0. So it's going to be 0 squared. And you get negative 4 over negative 1 equals the 4. So it works. You could have just plugged it in and it worked out fine. So that was an easy one. Move on to example 10. Example 10 says we have a limit as x, we have a trig limit, limit as x approaches 0 of x times sine of x over tan of x. So I would just try plugging it in. So it's 0 times sine of 0 over tan of 0. And you get indeterminate form, 0 over 0, which is indeterminate form. Okay, that's not good. So what could we do? You can try L'Hopital's rule, or we can try just simplifying. this stuff. The only thing I could see simplifying is the tan of x. So we can rewrite this as limit as x approaches 0. X times sine of x really can't change much, but tan of x is the same thing as sine of x over cosine of x, right? Now you have a complex fraction, so let's simplify that. Let's simplify just this right here. We'll just leave x alone right now. So what is sine of x divided by sine of x over cosine of x? What I could do is cross multiply. This would be and then 1 times sine of x is sine of x. Let's cancel, so you're left with cosine of x. So what we could do is rewrite this problem now as the limit as x approaches 0 of x times. So when you simplify this, this gives you cosine of x. Now does it work? I think it can work. Where have you seen it? So this would be 0 times cosine of 0. This is not in determinate form. Cosine of 0 is 1. 1 times 0 is 0. Now that's okay to have 0 as your number. 0 is technically a real number. So yeah, the limit as x approaches 0 is 0. That's perfectly fine. Let's move on to number 11. So number 11 says the limit as x approaches a of a squared minus x squared over a fourth minus x fourth. So I could try plugging it in. And this does not look good. It's going to be, so wherever you see an a, plug in a squared. So a squared is a squared minus a squared is a squared. And then a to the fourth minus a to the fourth. A squared minus a squared is 0. A fourth minus a fourth is 0. You have an indeterminate form. So not good. So the next thing I will do is, because it's a rational function, I could try factoring, right? It looks factorable. It looks like they're perfect squares. So I'm going to try factor. That's going to be the limit as x approaches a. And then a squared minus x squared could be factored as what? A plus x times a minus x. And then on the bottom, a fourth minus x fourth can be factored out as a square plus x square times a squared minus x squared. Could it be factored even more? Maybe the bottom, the top is good. Right, the top is good, the bottom, this can't be broken down because it has a plus, but a squared minus x squared can be broken down as, it's also a perfect square. It could be expressed as a plus x times a minus x. And what do you see that cancels? Let's see, a minus x and then the a plus x. Now you would get is the limit as x approaches a of, now on the top you're left with 1, and then on the bottom you're left with a squared plus x squared. Now you may replace your x with x squared, so it's going to be 1 over a squared plus, wherever you see an a, plug in x squared, so that's a squared. So A squared plus a squared is 2a squared. That will be your final answer. Number 12 is a strange one. It says, which demonstrates that f of x has an asymptote of y equals 2. So we kind of have to, they give us an answer. We kind of have to find out what is the limit question. So they're asking, what is a limit question when you have a horizontal asymptote of y equals 2? So when you're dealing with horizontal, that is your limit. So what you can say is, you can rewrite this as the limit as x approaches positive and negative infinity of your function. We don't know our function, so I'll just call it f of x. And your final answer or your limit should be 2. Okay, so that would be your answer. Okay, let's do another one. Last one for this section. Number 13 says, where is it not continuous? We have a piecewise function. Where is it not continuous? So uh, where do you pick up your pencil when you draw this? So how do you know something, for things to be continuous, you need a few things. So where is it not continuous? Well, first you need for things to be continuous. There's a few things that must happen. So the limit as x approaches a of f of x equals your limit. And the third condition states f of a must equal to limit. So what we're going to do is we're going to plug it in and compare. So I think it's like kind of the other one where the left has to equal to the right. So uh, so what we're going to do is plug in 2 into the second equation. We're going to plug in 2 in the second equation since they both have a 2. Yeah, do you see the equation? So we're going to so what we're going to do is we're going to plug it in and compare. So if you look at the first two equation, right? If you look at the first two equation, they both have the domain of x. They both have the x value 1, right? We have ln of x where x is less than 1, and then the other one is x minus 1 where x is between 1 and 2. They both have in common of 1. What we're going to do is plug in 1 into both of the equation. So it would be ln of 1, and then does that equal to the second equation where x is 1? So 1 minus 1. So ln of 1 is 0, and then 1 minus 1 is 0. So that's true. Now you got to do it with the second two equation, and you're going to use the x value. So we're going to plug it into this equation and this equation, and they both have a x value 2. So we're going to do that. So it's going to be 2 minus 1 equals to 2 minus, so I'm putting it in this one, 2. 2 minus 2 is 0, 2 minus 1 is 0. This is a false statement. We want them to be true. So it's going to be not continuous. But they have to be continuous everywhere. So where is it not continuous? Where is it not continuous? At the x value 2. That's all they're asking. Right? This is if you plug into second and the third, and you plug in the x value 2, the left is unequal to right, so that's not continuous at x equals 2. That's all they're asking. They're not asking where it's continuous. They just want to know where it's not continuous. Okay, so that's it for this one, and then we'll continue on with the derivative section. I will stop here.